So hi, hello, and welcome again. Today I'm going to start a new topic, and the topic is called excretion. How do you spell excretion? I'm starting off and it's already wrong. Excretion. I hope you can hear me properly. Maybe I have to move the microphone a little bit closer. Okay, so maybe that's a little bit louder for you. So excretion. This is basically the topic, and in the book it's on page 135 if you're using the Oxford IP Study Guide, okay, for the 2014 edition. Yeah, so if you're using this book, it's on page 135. So first of all, I'm going to talk a little bit of what excretion is, and then we're going to dive a little bit into the more specifics. The definition excretion is the removal of products of metabolic waste. Let's put it this way: metabolic waste. Now, what is metabolic waste? It's cellular waste. Okay, I'm going to give you two examples, e.g. one of them you probably already know is the removal of carbon dioxide, CO2. And how is carbon dioxide removed? Over the lungs, okay? Via the lungs. And the second example also called is nitrogen waste, and that's what I'm going to talk about in this topic. Nitrogen waste. And the nitrogen waste, at least in mammals, it's excreted over the kidney. So this is we will be talking after this introduction. We'll be talking about the kidney. Okay. Now, what about plants? Well, plants also have a waste product, and that is carbon dioxide. Yes, they do cell respiration, of course, and also oxygen gas from photosynthesis. So oxygen gas is a waste product, is a product. Yeah, it's a metabolic product, end product. And you might now wonder, where does the CO2, the carbon, come from that we are excreting over the lungs? Well, we eat food. This food is broken down by cell respiration. We have at the end carbon dioxide. This carbon dioxide then goes into the blood from the cells, from the blood to the lungs. It's then exhaled. Okay, so that's the food. I always say the lunch, the sandwich that you ate for lunch is now in the air in the form of CO2 because we're exhaling it. We're burning up the organic material, and then over the lungs we are excreting it. The question is now, where does the nitrogen waste come from? And this nitrogen waste comes from proteins that we eat. Proteins contain amino acids. Amino acids in long chains make polypeptides and proteins, and there is a lot of nitrogen there, and all of this excess nitrogen must be removed now. So mostly from proteins. Yeah, and of course, I mean, do I have to write this down? They contain nitrogen. So all of the excess nitrogen that we don't need has to be removed. It's not only the case in humans or mammals, but generally also in other animals. And this is what I would like to do now. I would like to compare the different nitrogen waste products. Nitrogen wastes. Products, because the end products, how the nitrogen is given off, is different from organism, to organism. Comparison is actually the better comparison of my English is not good today. The comparison of different nitrogen waste products. So I'm going to make a little table here. Actually, the table is also in the book, but I'm going to repeat this here because it's simply more organized this way. So nitrogen can be excreted in the form of ammonia. And the question is now, who does that? This is a freshwater fish. You should know these examples. And amphibia, the larvae. Tadpoles or frogs, for example. I mean, they also live in water. Okay, so in summary, ammonia is excreted by those organisms, those animals that live in water. The question now is some younger students ask me this: do fish pee? How do they pee? Yeah, how do they excrete? They want to know that. Well, they don't pee because what they do is they give off the ammonia over the gills. Okay, so it's directly given off. They don't swallow water, but there's water swimming in through the gills, and the ammonia diffuses directly from the blood of the fish into the water. Okay, there are a couple of points that I want to additionally want to make. So first we write down the organisms, and this is pretty toxic. Ammonia is pretty toxic, and but it is also very water soluble. That's why it can be given off directly. Okay, so it's and you need a lot of water because it's so toxic. Yeah? But that's not a problem. We've got plenty of water, much water needed. I mean, I don't know. Do I have to draw a fish now? Okay, so that's my fish. Okay, yeah, there are the gills here. Yeah, and the water with the ammonia goes in over the mouth. It comes out over the gills. Okay, then you have the ammonia being excreted this way, right? Yeah, so that's simply the thing that I want to clarify here. Yeah? So you need it must be very dilute. I've once had a home aquarium, and that is actually an issue. If you have too many fish and too few plants, then there is the danger that there is too much ammonia being built up, and that's not good. It actually harms the fish. Okay, so the next way of how ammonia is NH. It's NH3, and then in water, what it will form NH4 plus. You don't have to know this so much. I just want to show you that there is nitrogen in here. Okay, yeah, it's obvious. Yeah, just to see that there's N nitrogen in here. Yeah, urea is another way of it's another excretory product. This one can be found in mammals. Also marine, terrestrial, and marine. So for example, dolphins and whales, these are marine mammals, they also produce urea. Then also terrestrial and marine, and then also marine fish. They produce urea, and also adult amphibians, like frogs. Okay, adult amphibians, and the reason, yeah, so these are basically who makes them. It's less toxic. Yeah, okay, and you can. The thing is the following: you can excrete it in a more concentrated solution. Can be, and that's important. Excrete it in a higher concentration. This means less water is needed. Less water needed. Okay. So this is important for water preservation or water conservation. It's also one of the reasons why, for example, marine mammals like whales and so on, they produce this, because I mean they're living in salt water, okay, and they have to conserve, of course, their own fresh water as well. So that is the second one, and there's a third one, a third way how nitrogen can be excreted, and the third possibility is called uric acid. And uric acid is not toxic. No, we always have to say first which animals, so birds and insects. Ah, they are flying. They are flying. Yeah, and this is not toxic. Okay, and it can be excreted in a very high concentration, so you need even less water. Possible. How high? So high that actually it's not even liquid anymore. It is a paste. Yeah, it's a semi-solid paste. Semi-solid paste. Birds, the white stuff, right? The white birds, that's uric acid. And this is the reason why certain buildings are damaged, because it's an acid and it actually breaks down carbonate stones and can damage buildings this way, okay? Now, why is this important? Because birds and insects, because they have to fly, they cannot carry along too much water. Imagine birds peeing. They need that's a lot of water they have to carry along, okay? So this is the way that they are able to reduce the need of actually carrying along water. Yeah? So it's a semi-solid paste and it's not toxic. Yeah? So we also know this. Okay. So what is the general comment here? Comment or additional information is that the type of nitrogen waste is, of course, due to its evolutionary history. Due to evolutionary history, okay, even though whales and fish, they live in water, they produce different waste products, okay? Also, for example, there are other, I'll give you, beavers, otters. Where do they live? Yeah, they live. There's plenty of water. Okay, they live in water. What do they produce? Urea. They still produce urea, because all mammals produce urea. You might say, well, why do they do that? Maybe there's also different possibilities. Yeah, of course, but no, because they're mammals, they also produce urea. Okay, so this is the idea here. So you see that the different living things produce different nitrogen waste products depending on the environment that they live in. Yeah, so this kind of completes this chapter, not chapter, but this topic here. I move on, and I would like to talk about the next one. It's called osmoregulation. The regulation of water, osmosis, okay, you probably have heard, but osmoregulation is, refers to regulating water, okay, regulating the water content of cells or of an organism. There is this topic called homeostasis in chapter 6. We already talked about this. Homeostasis, and in homeostasis, an organism, that's actually one of the characteristics of life of all living things, is all living things are able to do homeostasis. They have to make sure that the inside is constantly maintained, and among other things is you have to maintain the water balance. I want to start off again with a little story here. Actually a sad story. Many years ago, must have been 20 years ago, I remember in the news it was actually that a couple of folks, a guy died because they were having a competition, a bet, stupid bet, and the one guy actually said, how much water can I drink? And the guy was actually drinking 15 liters of water in one session, okay? And he died, and then later on this was a news report, and the reason is because if you drink so much water, you're losing too many minerals, kind of all of the minerals. You're going to the toilet, of course, much more, and you're kind of losing too many minerals. This wasn't compensated. The guy had some kind of a nervous system problem then, and he died. Okay, so that is one example. So you take the body could not osmoregulate so much, or it tried to osmoregulate and then lost too many minerals at the same time. And then sometime later, I visited with my family. I visited the desert and in northern Africa on holiday, and we talked to the guy, a guy there who was kind of renting out those camels because we were doing this camel trip. And the guy said he's drinking. Guess how many liters of water every day? 15 liters of water every day. 15, same amount, but he needs that. Okay, so what I'm trying to say here is you see the amount of water that we need obviously depends very much on the environment, how much temperature is it there, and so many other things. And he's not drinking the 15 liters at once, but spread throughout the day. Yeah? So I just want to use this as a little example here, is that the water intake that we have and how much water we're actually losing. I mean, this of course depends very much on the temperature, on the environment, on what we eat, on how much salt we eat, and so on. Yeah? But it doesn't matter. We as humans or organisms, they have to maintain a certain water balance and by homeostasis, and this is called osmoregulation. Okay, so osmoregulation is one example of homeostasis. You have to regulate body temperature as well. Okay, so this basically means that excretion, like the removal of nitrogen waste, it's another example, yeah? But it is kind of bound to also maintaining the water balance. Okay, so when we pee, we're not only removing nitrogen waste, but we're also, of course, removing excess water. So I need to drink some coffee now. Okay, so let's move on here. There are two types of organisms called Osmoconformers versus Osmoregulators. And what is the difference? What we have here is the following. The question is how does the body internal or the cell internal solute concentration, which is salt concentration, e.g. salt concentration, okay, how does the internal solute concentration respond to the water around them? I need to explain this. With them I mean the organism. I give you the following here, an example. I'm going to give two graphs here, no numbers needed. Just, yeah. And on the x-axis we have the external, like in the water where the fish is swimming, solute concentration. Okay, same here, external solute concentration. Again, solute, that's the salt, for example. Okay, so like in salt water. And the question is the following here: what about the internal one? Internal solute inside the cell concentration. Okay, and in the first case it looks like this. When the external solute concentration goes up, then the internal solute concentration also goes up. So it kind of fluctuates, it goes along. Yeah? So what we have here is that these are called the Osmoconformers. I'm just going to draw an arrow here. Because the inside, yeah, if the outside, if this organism is swimming in a high salt concentration environment, then their cells will also have a higher salt concentration. And that's fine. Okay, and then the others here, with the osmoregulators, the question is, how does this look like? Okay, when the external solute concentration goes up, the internal solute concentration stays the same. That's basically what we have. Solute concentration. So they're regulating the salt concentration, right? So this is basically the two types of strategies on how different organisms can actually deal with different environmental solute concentrations or salt water concentrations. Okay. So this basically the Osmoconformers, they have a problem, however. Because what happens if the external solute concentration is so high and then the internal solute concentration also goes up much up, and maybe that's already too high for the cells. Okay, so yeah, so the problem here is okay, is with the Osmoconformers is that maybe you have a non-ideal a non-ideal internal solute concentration, because it's going up too much, right? They cannot regulate the amount of salt. And what we as humans, we are basically, we make sure that we try to maintain a constant internal salt concentration. What we have, there's also a problem here. Maybe you want to write this nicely, yeah, not into the diagram here, but somewhere we have more space. The problem is this requires energy. Energy needed. Excuse me. You need energy to do that because you need to remove the excess salt, or you need to maintain extra salt. So this is energy is needed to regulate. Okay, so that is pretty straightforward. So for example, we humans, of course, are an example of this. We mammals are and here what they say here is that the squids, for example, are an example here. I mean, they are living in water, but maybe they're floating around in going to different parts of the ocean. Some places have a higher salt concentration, some have a lower salt concentration, and instead of simply dealing with the different salt concentrations by adjusting the internal solute concentration, it just say, oh, who cares, I'm just going along. Okay, if the external salt concentration is higher, then I'm also going to just make it higher. Okay, so that's kind of their strategy. Yeah? So we now, actually, that's the example of dehydration and overhydration. This would actually, the example of this 15 liters of water would have actually fit better here. This is my mobile phone going crazy, in case you're hearing this funny sound. Okay, so dehydration versus overhydration. Dehydration versus overhydration. So I've actually given away my example already, but there are a couple of terms that you have to know. And this dehydration, overhydration refers a little bit to the osmoregulators. They have to worry about this a little bit. And there are three terms that I would like to talk about, and you have to know them. The first one is called isotonic. Isotonic. Maybe you've already heard of those isotonic drinks, those sport drinks. Okay, so this means that an external solution is isotonic to the internal one is if the solute concentration, the solute concentration is equal to the body fluids. So if you I don't know if you had those isotonic sport drinks already, and if you taste them, they taste kind of salty. The reason is because the salt concentration of the drink is the same as your body fluids. So when you're sweating a lot when you're doing sports, you're losing not only water, but you're also losing the minerals. And then how do you get the minerals back? It is by drinking things that contain minerals, and that's these isotonic drinks. They taste salty. Okay, but the salt concentration is the same as those of your body fluids, and so that's why they are isotonic, and that's why they have given those, say it's an isotonic drink. Okay, so and this is with the examples of the 15 liters. The guy who drank 15 liters of water was not isotonic. I mean, this was just water, tap water or mineral water. Yeah, there are some minerals in there, but the mineral concentration is way lower than what your body fluids have. Okay. So this, the second term is called hypotonic. Okay, hypotonic is if the external fluid has a lower solute concentration. Than the reference. Yeah, and in this case, the reference in this case would be the body fluids. So if you drink distilled water, then the distilled water is hypotonic compared to you yourself. It's not good. Okay. And the next one is called hypertonic. hypo and hypertonic. And that's kind of easy. Hyper is versus hyper is too much. Okay, you have a higher solute concentration than the reference. Okay, then the reference fluid. So basically I want to give you an example. Let's have we're gonna be doing this experiment sometime, and let's say you have a potato cube in here in liquid. So it's a potato cube, and let's say that over here we have a very high salt concentration, high NaCl, sodium chloride concentration. Then this high sodium chloride concentration, yeah, it is hypertonic in comparison to the potato. Okay, because it has a higher, so I just wanted to give you this, and then the liquids in the potato are hypotonic in reference to the external solution. Okay, what happens when you have dehydration? Okay, so let's move on. Dehydration is when dehydration. In dehydration is due to water loss. I know what you're thinking. That's clear, is this not? Okay. Yeah, but then you have to say it. Okay, if they ask you somewhere in an exam, define dehydration, you can. It's clear. It's because no, you got to define it. Dehydration is due to water loss from the body. Sometimes you have to state the obvious. Okay, always state the obvious first. You get a point for it. Okay. So the thing is the following. So what happens is due to water loss of the body, but salts are not equally lost. Normally, I've told you this example. Yeah, so basically what this means is, as a consequence, is the body fluid salt concentration increases. If you lose more water and you lose salt, so as a consequence, it becomes hypertonic. The body fluids, okay, they become hypertonic. So what do you need to do as a consequence of this? Yeah, as a consequence of this, you need, of course, to drink more water. Okay, you need more water intake needed. You become thirsty. Yeah. So that is the thing that I just want to make clear. You need because your body senses this. Yeah, so you're thirsty, what you have as well is not only more water intake that you need, but you need to preserve water. You need to conserve water. So what happens when you want to conserve water? You have more concentrated urine, less, but more concentrated. Of course, you don't want to lose more water. Okay. Urine. So the urine becomes darker. So you've probably already seen that the water, the color of the urine changes depending on how much you've actually had water, how much you drank water. Okay, but that's kind of clear. If you dehydrate, just think you don't even have to memorize this stuff here, because it's kind of obvious anyway. When you don't have enough water, you become dehydrated, you become thirsty, and of course your body is not going to produce as much urine because your body does not want to lose even more water. So you need to conserve water. And actually, overhydration, I don't even have to say this, is when you have too much water, when you drank too much water, so it's due to excessive water intake. Okay, due to excessive water intake, and then you're overhydrated, and what happens is the body fluids become hypotonic. Body fluids, like for example the blood, okay, is hypotonic. And the consequences, yeah, actually it lists it, it's actually even listed in the book. Behavior changes, confusion, drowsiness, delirium, blurred vision, muscle cramps, nausea, seizures, coma, and death. Here we've got it. Okay? So overhydration can lead, if you to death, if your body is not able to deal with that. Okay? Yeah. So too much water is also not good. Yeah. Because one of the reasons is that you also tend to lose, of course, even more minerals. You go run to the toilet more when you drink too much water. So the idea is the following, folks. Yeah, they always tell you drink a lot of water, you should, but you don't force yourself. If you feel that you don't want to drink something because you've already had enough, then you don't drink more. You don't fool around. I mean, there are some folks who really think they're really funny. They want to go into the Guinness Book of World Records, and they end up doing stuff like this, which is just plain stupid. You don't do stupid things using food. I mean, I remember this one case, just the last story. We just have to shake my head. He wanted to go into the Guinness Book of World Records, and he ate a bicycle. I'm not making this up. This is how do you eat a bicycle in the world? Yeah, he bought himself a bicycle and he ground it up into powder, and then with his normal food he always ate a little bit of his bicycle. I mean, come on, folks. How stupid is that? I mean, you don't play with your health like this, okay? But yeah, it's kind of pointless. Yeah, so you don't play around with food and drinks and water and how much you can drink and how much you can eat, and no, don't do that. Okay, it's there are other ways of making your life more interesting. Okay, I just have to say it. Had to get it off my heart, and with that, I think I'm just gonna say, see you around. Bye bye. Bye bye. Bye bye. Write your nice notebook.